Okay, let's begin. So, numerical methods of solving for mathematical problems. Whenever analytical methods fail, that's when we use numerical methods. And that is, analytical methods, you're not able to actually solve by analytical methods. Then we solve by numerical methods. So mainly it is for equations. So first is algebraic equations and non-algebraic transcendental equations. We have numerical methods. Then for derivatives also we have numerical methods for doing derivatives, and also for integration and for solving differential equations. So these are the four major things that we will be dealing with numerical methods. Of course, matrix methods of analysis is also sometimes it is taken as part of the numerical methods, because we deal ultimately we reduce all differential equations into linear form and then convert it into matrix form and then do it. So that's why matrix methods are also important. We begin with the first part, solving for roots of equations. So yeah. So the very first one is numerical methods to finding roots of equations. So all of which are iterative. So they are iterative methods. That means trial and error methods. And these are the four: bisection, regular falsy, secant method, and Newton-Raphson's method. So one by one we'll take up. First method is the bisection method. So I'll explain the bisection method. So bisection method, this is the first of the numerical methods to solve an equation. Now, this method is based on intermediate value theorem, which states that a function f of x is, if it is continuous between a and b, and f of a and f of b are of opposite signs, then there exists at least one root between a and b for definiteness. So this is like this. Let's take an example. Yeah, let f of a be negative and f of b be positive. Then roots lie between a and b. So let us, this is x, this is y, and we are dealing with the function y is equal to f of x. Now, let us say this is point A and this is B, and function value at A is negative and function value at B is positive. And function is continuous and differentiable. So then let us say now, so one thing from intermediate value theorem, this is clear that between A and B, there will be at least one root, if not more. There is at least one root. Let us say this is the curve. There's at least one root. Which is the root? This is the curve y equal to f of x. Wherever curve cuts the x-axis, this is the root. So this point is the root. Just hold on for a minute. I have a call. All right. Sorry for the disturbance. So okay. So in this bisection method, so we are sure that f of A and f of B are of opposite signs, then there will be one root. So how do we proceed? This is a iterative step. That means again and again we have to keep doing this. So we need to find x such that f of x is 0, and given is this condition, given condition is that f of a and f of b are of opposite signs. And so therefore root lies in open interval AB. That is for sure. So now what we do, now what we do is, now we keep changing the pivot. So let x naught, we say x naught is a plus b by 2. So we bisect, this is bisection method, right? So we bisect the interval. So this becomes x naught. Now, after that, we check the sign of, check if f of a into f of x naught is less than 0, then root will lie in a comma x naught. All right, this becomes our new interval. Okay, therefore new interval is a comma x naught. Now, on the other hand, if this fails, else if f of x naught comma f of b is less than 0, that means f of x naught and f of b are of opposite sides, then root lies in x naught comma b. Therefore new interval x naught comma b. Of course, there is one case. Now first we have to do this. If f of x naught equal to 0, then we have identified the root x naught. Exactly halfway we have identified the root, we can stop the iteration. Now what we do, now repeat this process. Okay, so if we have not got exact root, repeat this process till the accuracy that we desire. So how it happens is like this. So a comma x naught. Now again, so in this particular figure that we are seeing, AB, we come to the midpoint of this segment AB. So x naught is a plus b by 2. Now f of a into f of x naught, f of a is negative, f of x naught is positive. So again, because root will lie here, we divide this into, again bisect this interval. Now from x naught we come to x1. All right, and again we do this test from a to x1 and x1 to x naught. So again here we find that f of a and f of x1 are of opposite signs, so root will lie in between. Then we again bisect and we come to x2. So now we find that the root lies between x2 and x1. So if it lies between x2 and x1, again we bisect. We bisect this and we get x3. So by this, by repeating this process, what happens is, and say nth iteration, you get xn. You get nth iteration, you get that between xn minus 2 and xn minus 1 root exists, let us say. So then xn we find out as x n minus 2 plus x n minus 1 upon 2. Now this n can be how much accuracy we want, that much we can take. N we can take up to 10. That means 10 iterations. So we will get closer and closer to the root. We make 100 iterations, you will get very, very close to the root, if not directly equal. Okay. So this is the bisection method of iteration. We find the solution in this way. So x1 and x1 will be the new interval. I'll just show this. There's important consideration here. Now, as before, this is bisected at x1 and new interval will be exactly half the length of the previous one. We repeat this process until the latest interval is as small as desired, say epsilon. It is clear that the interval width is reduced by a factor from 1/2 at each step, and at the end of nth step, the interval will be of length. So it is an bn will be the new interval. So of the length bn minus an by 2 power n. So original length was b minus a. So divided by 2 power n. So then we put a condition that modulus of b minus a by 2 power n should be less than or equal to epsilon. So from here, we find the logarithm. This is, yeah. We find, use the logarithm and find out n. What should be the value of n? So number of iterations required to achieve accuracy of epsilon. So these many number of iterations will be required. So here it is, calculation is simple. B minus a by 2 power n less than or equal to epsilon. So 2 power n will be greater than or equal to b minus a by epsilon. So n will be greater than or equal to log to the base 2 of b minus a by epsilon. We have to use modulus, so epsilon will also be positive. Okay. Now we can convert this to natural logarithm. So this is the number of steps required. Now this is a standard algorithm. So we write a code in a computer. We use either MATLAB or in Excel also you can do, or any of the language you can use. any of the programming language we can use and program this. And after n steps, it will, wherever we want to truncate, we'll stop. So this is the bisection method. This concept we need to understand clearly. Next, in bisection method, we go half by half. But in the next method, we call it as the regular falsy method. This method, we use a different technique. We will see this. So this is the iterative steps that are given. This is called as the false position method or regular falsy method. So this method starts with taking guess, unlike the so this method starts by taking two guess values, x0 and x1 for roots, just like bisection method. And we find f of x0, this is not x0, there. F of x0 and f of x1 less than 0. Then we do an iteration formula. Okay. What is this iteration formula? Is this? Let us show this by an example. How do you get this? Now the iteration formula here, there's an error. I will write the exact iteration formula. Now, instead of going by bisection, what we do is, let us say, this is some value x0, this is say x1, and this is the function value. These are the 2 points. So now what do we do is we try to make a straight line approximation. Now, assuming that this is a straight line, so this is a chord we are taking. This point here, the coordinates of this point is x0, comma f of x0, let's say. And this coordinates are x1, comma f of x1. So we write f0 and we will write this as f of x1, we will write as f1. Okay. Now, how to come close to this point? To come close to this point, we choose the second iterative point, x2, as this. The point where y becomes 0 on this straight line. So what we do is, equation of this line will be y minus y0, that is f0, y minus y0 is equal to the slope Now we have to put, so this is the straight line joining these 2 points. Now put y equal to 0. So what we get, x will be equal to x naught minus x1 minus f naught times x1 minus x naught upon f1 minus f naught. So this we will simplify. X naught f1 minus x naught f naught minus f naught x1 plus f naught x naught. So this cancels. This is our x2. So x2 becomes this. This is our x2. Put y equal to 0. So we get f1 x naught minus f naught x1 by f1 minus f naught. Okay, so this is f1 x naught minus f naught x1 by f1 minus f naught. So now the interval now is reduced. We don't take the bisection method. We take this x2 as the iterative step. This is our next false position, that assuming that root is here, you check f of x2 and f of x naught should again be of opposite signs. If they are of opposite signs, again what do we do? Next step is join these two. So now x naught now the next iterative step will be here, x3. So x3, when we find, it will be f2 whatever is the next this thing, f2 minus x whatever is the next iterative step here, to f1 x2, here it is taking x1 okay, this has taken a step like this. So for me, in this particular case, I will get x naught only. So we get like this, and if root is such that we are bisecting. If we are going, see, generally we go either, depends on whether the function is going downwards or upwards. We'll go closer to the root. Now we are going leftwards, otherwise we'll come rightwards. So for example, if the curve is like this, and this is our x naught, and this is x1, then this will be x2. In this particular case, then we'll have to choose x0 and x2. So always that check will be there, and in every step, whatever you choose as the new interval, okay, that in the new interval, again this chord we need to check, this will be x3. Like that, we'll keep going close to the root. So either we move this way or, we move this way, closer and closer to the root, closer and closer to the root, like this. So this is a regular falsy method in which we, by number of iterations, we come closer to the root. So in the first, this particular case that we are choosing, the nth or n plus first iteration will be fn minus x naught minus f naught times xn by fn minus f naught. So this will be the iterative step. Now this is faster compared to the bisection method. And because in bisection method, you don't know where the root is. But in this method, we'll exactly keep coming to know which subset of the interval root will lie, and we'll go a little faster. The number of iterative steps that is taken for the same amount of accuracy will be lesser in regular falsy method. Now, after the regular falsy method, so like bisection method, regular falsy method is 100% reliable and root will always be found, since x0 and x1 are taken on the either side of the root. Root is kept trapped between x0 and x1 in both bisection and regular falsy method. Okay. Now both, this is important. I'll anyway clip it for your notes. This is multiple choice concept wise. These statements here are very important. Now both bisection method and regular falsy method are first order convergence, all linearly convergent. This is important. Now secant method and Newton-Raphson method have convergence rate 1.62 and 2. So Newton-Raphson method is quadratic convergent. Secant method is in between 1.62. So bisection and regular falsy method are first order convergence. That means you are approaching at a linear, you're making linear approximations. So next, look at the secant method. Secant method, it is slightly different. This is much faster than the previous two methods. Secant method proceeds similar to regular falsy method in the sense that it also requires two starting guess values. But the difference is that the product f of x0 and f of x1 need not be negative. That is, at any state of iteration, we do not ensure that the root is between x0 and x1. However, secant method uses the same iteration equation as regular falsy method. What is secant? It is a chord. Extension of a chord is a secant. So let us see this. No figure is given here. I'm drawing a figure. So let us say this is the function y equal to f of x. So now we assume 2 points. Now we don't have to worry that they should be of opposite sign. Function value should be opposite sign here. No, here need not be. We have these two. Now what we do, we draw a chord between these 2 points. When we draw a chord and extend that chord, extension of a chord is called as the secant. So the third point that we get is this point. So again, we do a straight line approximation only. Okay. However, now we don't have to worry where this point lies. As long as we keep doing this, we converge to the solution. X1, this is X2. Again, X2, we get the same. F1 times X0 minus F0 times X1 by F1 minus F0. Now, next, we take X1 and X2 as this is as the new chord. So when we take this as the new chord now, so you look here, we are approaching closer to the root in very easy way. So now this is X3. Then what we do, we go for next chord or the secant. And see here, we have almost reached close. Let's say we are to the right. Then what we do, this is X4. Then we take X3 and X4. And then draw a chord. X3 and So again, we draw a chord and again we come closer and closer. So in this, the nth iterative step will be not in terms of x naught, and it will be f of n into x into n minus 1 minus f of n minus 1 times xn by fn minus fn minus 1. Okay. Remember, the first step was x2. First assumption was x naught and x1, and then we say the closest root is x2. Next, that means this is the first step, is x2. Second step, we get x3. Nth step, we get xn plus 1. So depends on how accurate we want. We keep on adding steps. So this is secant method. This is a secant method, like regular falsy method. Only advantage of secant method is we do not try to ensure that the root has to lie in between x0 and x1. Whereas in both bisection method and regular falsy method, we have to ensure that the root lies between both within the interval. So this has an added advantage, secant method. Now, next is the case so here, this is a important note from concept point of view, you should know this. Geometrically, both regular falsy and secant method find x2 in the same way. That is by drawing a chord from x0 comma f of x0 and x1 comma f of x1. An intersection of the chord with the x-axis is x2. The advantage of secant method is that it is faster than both bisection and regular falsy, as it has a convergence order of 1.62. However, the disadvantage is that secant method is not 100% reliable, since this equation will fail if f of f1 is equal to f0. That means if secant method, the function values, if they are same, then the chord you will get is a horizontal chord. And you will never find x2. x2 will be a point at infinity. So now if f1 equal to f2, now which may happen since no effort is made to keep f1 is equal to f0 to be of opposite signs, as it is done with regular falsy method, which uses the same iteration. So this is the disadvantage of secant method. Although it is faster, the rate of convergence of regular falsy method is 1. The rate of convergence of secant method is 1.62 convergence order. Next is Newton-Raphson's method. For this, of course, it should be a differentiable function in essence. However, we use the Taylor series approximation. So there's the fourth one, Newton-Raphson method. This method is generally used to improve the result obtained by one of the previous method. Let x naught be the approximation of the root, and let x1 is equal to x naught plus h be the corrected root, so that f of x1 is equal to 0. So what we do, we expand using Taylor series. So the Taylor series expansion of the function about x naught is f of x naught plus h times f dash x naught plus h square by 2 factorial times f double dash x naught, so on, and this should be equal to 0. Neglecting the higher order terms, that means these higher terms, and just taking the first, the constant term and order of h is 1 equate to 0. So this gives h is minus f of x naught by f dash x naught. So basically what we have done, we f dash x naught is the tangent. I will show by figure what does this mean, how we get this, what this solution means. So a better approximation than x naught is therefore given by x1, where x1 is x naught plus h is equal to x naught minus f of x naught by f dash x naught. Successive approximations are given x2, x3 up to xn. Xn will be xn plus 1 will be xn minus f of xn by f dash xn. So this is the Newton-Raphson formula. This particular one is the Newton-Raphson formula. So the order of convergence, the error term here, we're not going to get into the how to find this error term. Error term basically means this term, the second order error term. So Newton-Raphson method had second order or quadratic convergence. Now what this means is this. If I can have a figure. Yeah. So this is y equal to f of x. So I start with x naught. What I do, I draw a tangent at x naught. Okay. So we know that f dash x naught is the slope. Now y minus f naught, okay, or f of x naught is equal to slope into x minus x naught. Now we want to find where is y0. That point will be x1. So put y equal to 0. We get x is equal to x1. So x1 is, you see here, when you put y equal to 0, it is x naught minus f of x naught by f dash x naught. So what we have done is we drew a tangent. Instead of secant, now we are drawing a tangent at that point, and wherever the tangent cuts the x-axis, that will be our x1. This is x naught. Now next, at x1, this is x1 comma f of x1. Again we draw a tangent. Now the equation of this tangent, this equation of tangent at x naught comma f of x naught. Next we draw, we use equation of tangent at x1 comma f of x1. So y minus f of x1 is equal to f dash of x1 into x minus x1. So now put y equal to 0 and x becomes x2 now, the next step. So x2 will be x1 minus f of x1 by f dash x1. So this is how you have to derive the steps. So like this, nth step will be xn to f of xn by f dash xn. Only thing is, function has to be a differentiable one. And very quickly we are going, because we are using tangents, we go very fast to the root and we get the root of the equation. So this is the Newton-Raphson's method. The error, or the approximation from one step to the other step is this. H is this, minus of f of xn by f dash of xn. Okay, let us try to do some previous year's question papers, questions on this, and see the solutions. So solution to equations, these are questions from previous GATE. Some of them are common sense, some of them are roots, but we need to practice all of them. So practice problems. Now in the interval 0 to pi, the equation x equal to cos x has how many solutions? So this, we don't need the full concept of any of this thing, but just a common sense. We only need the intermediate value theorem. We know that cos at pi minus pi by 2 is 0. At 0 it is 1. At pi by 2 it is 0. And at pi it is minus 1. So this is a rough sketch of the cos x graph. So this is pi by 2, this is pi. Now the question is, it is not just cos x, it is x equal to cos x. So we have to draw two graphs, y equal to x and y equal to cos x. So this is y equal to cos x. And this line, next one, will be the line y equal to x. Y equal to x line is a 45-degree inclination line. And between 0 and pi, we see that this line will cut the curve only at one point between 0 and pi. So just graphically, we see and say that this has one solution. Exactly one solution. So that's it. So it's exactly one solution. Okay, let's do the next question. So here we didn't use any of the numerical methods concept. It was more of a common sense. Now again, we use this basic concept. So this one, the polynomial p of x is x power 5 plus x plus 2, has all real roots, 3 real and 2 complex roots, 1 real, 4 complex roots, all complex roots. So nature is how to identify a polynomial. So polynomial equations, very important. All polynomials, fundamental theorem of algebra says that polynomial of nth degree will have n roots, and complex roots always occur in conjugate pairs. That means if they are complex roots, they will be either 0 complex roots or 2 complex roots or 4 complex roots, so on. Okay, so here in this particular case, this is x power 5. So it has 5 roots for sure. Now complex roots can be either none, all 5 may be real solutions. Next, we may have 1 real, 4 complex, or 3 real, 2 complex, like that. So either 0, 2, or 4 complex roots. So real roots can be 5, 3, or 1. Now, which one? How can we identify that? For that, let us differentiate this expression. We have to use the concepts of calculus now. Now, p of x is x power 5 plus x plus 2. What is p dash x? 5x power 4 plus 1. Now, this is always greater than 0 for all x belonging to R. That means, that is, because the first derivative is always positive, which means p of x is a strictly increasing function. Correct? A strictly increasing function will never come back. So now where exactly is the root? That also we can say p of 0 is 2. That means x equal to -1 is the root. We can, by inspection, I have just said x equal to -1. It's -1 plus 2. So I have directly found the root by inspection, just my guess. And here at x equal to 0, it is 2. The function value we like this. It is continuously increasing. That means once it cuts the x-axis, it will never cut the x-axis again, just because of the first derivative test, which means it will have only one real solution. It will have only one real solution. Remaining 4 roots will be complex. So answer is C. So what logic did we use here? Nothing. We just use that polynomial of degree n will have n roots. Okay, some real, some complex. Complex roots always have to occur in conjugate pairs. So that we checked, and then when we differentiated, we found the function to be strictly increasing, which means if it cuts the x-axis, it will cut x-axis only at one point. Therefore, it will have only one real solution. The remaining 4 will be complex roots. It will not be able to trace them on the real plane. Okay. Next. Okay, this is easy. These are all basic roots of the equation. Numerical methods we have put it, but we have never done these problems elsewhere. That's why we are doing it here now. Now, given that one root of the equation is 5, then what about the other roots? So, simple. Ax cube plus bx square plus cx plus d equal to 0. Sum of roots in this case is minus coefficient of x square by coefficient of x cube. The sum of the product of roots taken 2 at a time is c by a. The product of the roots is minus d by a, alternative. Of course, if it is a quadratic, this is a cubic equation. This is for a cubic. We should know for a biquadratic, okay, 4 roots. So sum of the roots, again, it will be minus b by a minus coefficient of x cube by coefficient of x power 4. Product of roots taken 2 at a time, 4c2, you will get 6 terms basically. I'm leaving it here. This will be c by a. Then product of roots, their sum taken 3 at a time. Minus d by a, and product of all the roots taken together is e by a. So observe what we are doing. The first sum of the roots, it will always have minus. Then the next immediate higher product will be having plus sign. then the next higher product again will have a negative sign, and the next higher product will have a positive sign. And the coefficients is just keep going by the higher the coefficient. So B by A, next is C by A, next is D by A, then E by A, like this. So we have to use this here. So one root is 5. So sum of the roots has to be minus B by A. Sum of the roots has to be 10. So 1 alpha plus alpha 2 plus alpha 3 must be minus of B by A, so plus 10. So alpha 1 is given to be 5. So the sum of the other two roots has to be 5. So alpha 2 plus alpha 3 should be equal to 5. Now here only we can check. 2 plus 4 is 6, gone. 3 plus 4 is 7, gone. Minus 2 minus 3 is minus 5, not plus 5. So in the first step itself, we can identify that 2 and 3 should be the roots, other two roots. Another way to check is 5, 2 into 3 into 5. Of course, this is 30 you get, but you don't have to go this far. The first step itself is sufficient. So next. Now it is known that the two roots of the nonlinear equation are 1 and 3. Then the third root will be. Now this third degree cubic equation and two roots are real. So that means the third root also has to be real. There is no question. Third root has to be real. Because if it's a complex root, it has to occur in conjugate pairs. Because this is a polynomial equation with real coefficients. The coefficients do not have I term anywhere. So they are real coefficients. So the roots will have to follow that. If it's a complex root, it has to be in a conjugate pair. So now the third root will be, see, the sum of roots is 6. So B by A, 6. Now 1 and 3 are the roots. So naturally the third root will be 2. 2 will be the third root. It's just a common sense logic. So far all were nothing on the 4 methods that we discussed. Now comes the questions on the 4 methods. So the iteration formula to find square root of a positive real number. Square root of a positive real number by Newton-Raphson method is, so f of x is square root of x. And what is this b now? B will be the iterative step anyway. So the question, there is some missing term. Okay, I think B, square root of a positive real number B. That is the question. What is the approximation? So x equal to B. Now, how to find the square root? So we start with x naught and say f of x naught. So f of let us see. So x naught and root of x naught. So according to this, the first step is x naught minus f of x naught by f dash of x naught. So x naught minus root x naught by what is x naught is B. F of x naught root B. I will see what I can do. F dash x is 1 by 2 root x. So f dash x naught will be 1 by 2 root x naught. So just a second. Just one. Okay. Just a second. See, other way to do this for a positive real number. Select let f of x be x square minus b, and x has to be a positive number. Okay, this is now f dash x will be 2x. If we get a solution for this, we'll get f of x equal to 0 will imply x will take plus or minus root b. We are interested in plus. Now, the iterative step, Newton Raphson's iterative step is this: xn minus f of xn divided by f dash xn. So we get xn minus f of xn is x square minus b divided by 2 times xn, like this. So we get 2xn square minus xn square plus b by 2xn. So this is xn square plus b by 2xn. Now, yeah, look at this iteration now, step of the options that are available. Xk plus 1 is x square plus b by 2xn. So this is our solution. So this is the iterative step for Newton-Raphson's method. Okay. All right, this is the iterative step we need to calculate for the next one. So let x minus cos x be the function. That means we are solving for cos x equal to x. We want to find the root of this expression. Root of this equation, f of x equal to 0. So what is the iteration point? Same iteration point. Xn plus 1 is xn minus f of xn by f dash xn. This is Newton-Raphson solution. So how to find this? So xn minus f of xn is xn minus cos xn by what is the first derivative? F dash of x is 1 minus 1 plus sine x. 1 derivative of cos x is minus sine x. So 1 plus sine x. So 1 plus sine x power n. So we get xn plus x sine xn minus xn plus cos xn upon 1 plus sine xn. This is gone. So this is xn plus 1 is equal to, this is xn by the way. You have xn sine xn plus cos xn by 1 plus sine xn. Okay, this is the iterative step. Okay. All right, this the the Newton-Raphson iteration formula for finding cube root c. So take x cube minus c, f of x as x cube minus c, and then you do it. I'll put this, you try it later, but you can easily do it. Right now, you please do and tell me the solution. Choose f of x as x cube minus c. F dash x will be 3x square. So Newton-Raphson's iterative step, xn minus so 3 minus 1 will be 2 plus c by 3xn square. This will be the solution. D is the solution. No, plus, sorry, C is the solution. Okay, so this is the solution. So many questions on Newton-Raphson's only. So you can understand how they are important. Now, there's an interesting question. If the first iteration starts at a negative number, then what is the solution? Now we have already done for the square root here. So f of x is x squared minus 2, f of x is 2x. We get xn plus 1 is xn minus f of xn by f dash xn. You don't have to do further. Here itself we can check this. F of xn is x squared now. If we simplify this further also, we start with you get 2xn square minus xn plus 2 So we are getting half into xn plus 2 upon xn. This is what we get. Now, if we start with a negative iteration, if we start with x1 is equal to -1, x2 will be a negative number only, -1.5. Now x3 will be -1.5 plus -2 upon 1.5. So again, you will get a negative value as the iteration. So like this, it keeps going on and it converges to -√2. Correct answer is √2, that is 1.414. So it will converge to -√2. It will not converge to +√2 because see, the iteration started with a negative here. So we need to be careful in this one. So we should examine, we should cross check like that. So all the question is on Newton-Raphson's only. The Newton-Raphson method is used to find the root of equation and f dash is the derivative. The method converges to. The method converges always only if f is a polynomial, only if f reduces to only if f is negative, none of the above. Okay, this is an important question. We didn't discuss about this part in our discussion. Whether it converges always, we cannot say. Yes. Okay. The answer is this will converge if the approximation that we choose, the first approximation should be close enough to the true solution. If it is too far from the true solution, this will not converge. That is with the Newton-Raphson method. So in NR method, the method converges if initial approximation is close enough to the root. or this should happen. Basically, what we are doing is f of x by f dash x. This modulus should be less than f dash x by f double dash x. So the next ratio of convergence. So our chosen approximation should be such that this is valid. Okay. So this is an important part of Newton-Raphson's method. If it is very far away, it will not converge. It will diverge. You will have to choose a value close. And it so much depends on the initial approximation that we choose. Look at the next one now. This is given a greater than 0, we wish to calculate its reciprocal value 1 by a by Newton's Raphson method for f of x equal to 0, for a equal to 7. Not just f of x equal to 0, the question is slightly different. Okay. This f of x chosen is f of x is the f of x has to be defined here. Is it x minus 1 by a? Usually we don't choose that way because we are choosing a reciprocal. We will choose this way. Let f of x is 1 by x minus a. No, this has to be, f has to be specified. If it's not specified, we can choose like this. So now f dash of x here will be minus 1 by x square. So xn plus 1 is xn minus f of xn by f dash xn. So this is xn minus 1 upon xn minus a by minus 1 upon xn square. So this is xn into minus 1 upon xn is minus 1 by xn No, plus 1 by xn minus minus anyway, plus 1 by xn minus a. So here we get 2 by xn so we get 2xn minus a xn square. So this is our iterative step. Now the first iterative step for a equal to 7, a is equal to 7. So xn plus 1 is 2xn minus a xn square. Now for n equal to, starting with x naught is given to be 0.2 and a is given to be 7. So x1 will be 2x naught minus 7x naught square. That is 2 into 0.2 minus 7 into 0.2 the whole square. This is 0.4 minus 7 into 0.04. So 0.28. We get 0.12. That's the first iterative step. So you have B or C. Now let us look at the next iterative step. X2 will be 2x1 minus 7x1 square. So you will have to do this 2 into 0.12 minus 7 into 0.12 the whole square. This is 0.24 minus 12 square is 144. 7 4 28, 7 4 28, 30. So we get 1392.1392. So this is the correct answer. This is the first step. This is the 0.1392. Of course, here the question, they should give what is f of x. Otherwise, it will be difficult which approximation function we are taking. That is important. Okay, this is again the same formula. Same formula. So we have to use this. F of x is 1 upon x equal to a, and we get this. Starting from x naught equal to 1, let us do this. So all the questions are on Newton-Raphson's, not even one on bisection, regular falsy. So starting from x naught equal to 1, one step of Newton-Raphson method in solving the equation gives the next value x1 as. Very simple. So we need to find a solution for f of x equal to 0. X cube plus 3x minus 7 equal to 0. F dash x is 3x square plus 3. So x equal to 1 is the starting point. So x1 will be x naught minus f of x naught by f dash x naught. I don't have to do the full calculation, that's why 1 minus f of x naught, put 1. 1 plus 3 is 4 minus 7 is minus 4 by f dash. So f dash x1 is 6 here. So I get 1 plus 4 by 6. 1 plus 2 by 3, that is 0.667. I think this should be the answer. Saying 1.5. I'm sorry, this is 3. This value is 3. I made a calculation error. 1 plus 3 is 4 minus 7 is minus 3. So this is 1 plus half, which is 1.5. So x1 is 1.5. X1 is 1.5. So Newton-Raphson method to find roots of an equation f of x equal to, this one important, 13th. For solving algebraic and transcendental equations, which one of the following is used? Euler's method, Stokes theorem is a theorem for vectors. Euler's method is for differential equations, not for algebraic and transcendental equations. Coulomb's theorem does not belong here for this. So Newton-Raphson method is the method that is used. Now, Newton-Raphson formula to find roots of an equation f of x is, of course, direct iteration. We have to remember this: xn plus 1 is equal to xn minus f of xn by f dash xn. So next, the real root of the equation x e power x equal to 2 is evaluated using Newton-Raphson's method. If the first approximation of the value x is 0.8679, the second approximation of the value x correct to 3 decimal places is. So we can do this. So f of x is equal to x e power x minus 2. So f dash x will be e power x plus x e power x. Now, the first approximation is x naught. We have taken as 0.8679. So what will be x1? x1 will be x naught minus f of x naught by f dash x naught. So this is what we need to calculate. So 0.8679 minus, let us calculate this one. We have to use a calculator. So x is 0.8679 times e raised to 0.8679 times, okay, I think if we do a simplification, it will be easier for the calculation, but still, this is 2.06725. No, we are truncating it so much, we may get errors. That is why concern. If we simplify, xn is xn plus 1 is xn minus f of xn by f dash xn. So we get xn e power xn minus 2 by e power xn into 1 plus xn. When we simplify, I'm just trying to see. Xn e power xn plus xn square e power xn minus xn e power xn plus 2. I think it's still more complicated. Still more complicated than the earlier one. Okay, let's do like this. Now, e raised to the power 0.8679, 2.38190 multiplied by 1 plus x. So 1.8679. So we truncate to 5 digits, 4.44916. So 4.44916 is 57. So 2.06 725 divided by minus 4.449179157. Okay, so 0.46, the negative. Oh. How to go back? 2.06725 divided by 4.449157. Okay, I negate it, plus 0.8679. So we get 0.40326. You're not getting.
Sir, in f of x, in f of x naught, we need to do minus 2, like 2 point.
Okay. I didn't do that. Oh, I didn't do that. Huh? So this is 0.006. Okay, I made that mistake. Okay. So if that is the case, 0.06725 divided by 4.449157. Take a negative, plus 0.8679. So we get 0.852784. So to approximating to 3 decimals, 0.853. So 0.853. All right, so most practically all the questions every year is on Newton-Raphson's. All are Newton-Raphson's only, and all are solutions like this. So we will stop here for today. Tomorrow's class we will do integrations and other solutions. Okay, this is one. Okay, I'll be sharing this with you. You please practice. I've asked one of my colleagues who is helping with me to share with you a book on which all the questions, there are questions and answers, and from each chapter you can take, because you will not have enough time to do all the questions of all the chapters. So you can do some selective questions from each chapter and solve them. So I have to check with him whether he shared the link with you. I'll ask him to do it again. So tomorrow we will do integrations and we'll go for differential equations. That will be the but Newton-Raphson you have to be thorough with. A definite question and they're asking, and integration is also easy one. So we will do further questions. Tomorrow we'll start the class at 4. Okay, thank you. So just a second, I'm stopping with